Hello, my name is Mr. Feld, and today I'll be explaining to you step by step how to solve a problem from your grade 12 Advanced Functions textbook. The question is located on page 113 and it's question 13, so let's get started. Okay, so the question is explain how to determine the value of x that gives a maximum for a transform sine function in the form y equal to a sine of kx minus d plus c if the maximum for y equal to sine x occurs at 91. Some key things to highlight in this question are we're explaining how to determine the value of x that gives a maximum for a transform sine function in the form y equal to a sine of kx minus d plus c if the maximum for y equal to sine x occurs at 91. Each highlighted point is important, and the value of x and the maximum are just points on the actual sine graph. So the value of x is when it happens, and the maximum is the highest value of y on the actual graph. Before we get to an example, I'm going to be going over what y equal to sine x looks like graphically, and then I'm going to be going over transformations of a sine function. So that would be this right here. So first we're going to be going over properties of base sine function. Okay, so the first property of base sine function is they have a smooth curve that repeats every 2 pi radians, and this goes on forever in the negative domain and positive domain. So you can see a smooth curve that will repeat every 2 pi radians. So in one cycle from 0 to 2 pi, and then another cycle, you would end up at 4 pi, and this would go on forever in the positive domain, negative domain. The next property is they're continuous functions, so no interruptions with the value of x. So you can see that there's no breaks in the values of x. The next property is they have a maximum point of 1. So you can see a maximum point of 1. The next is minimum point of negative 1. Negative 1. And you have to remember that this is in the value of y. So on the y-axis. The next property is equilibrium, which is the average between the maximum and minimum. So for base sine graph, or sine function, it's always 0. Since the maximum is 1 and negative 1, you take the average at 0. And the equilibrium is always aligned, so in this case it's y equal to 0. And finally, the amplitude. The amplitude is basically a distance from the equilibrium to your max and min point. So they have to be the same. So from the equilibrium to the maximum and equilibrium to the minimum, same. They're the same. So for base sine graph, it's always 1. Now the key difference between a positive sine graph and the negative sine graph is a reflection in the x-axis. So they are flipped in the x-axis. how this affects when your max point occurs, in a positive sine graph, the maximum will occur at pi over 2 radians. In the negative sine graph, your maximum will occur at 3 pi over 2 radians. So the key difference is the reflection in the x-axis. The next thing I'm going to talk about is transformations of a sine function. Okay, so there are really only 4 factors that affect the transformation of a sine graph. So you have the a value, the k value, the d value, and the c value. Y is just the dependent variable and x is the independent variable. So the a value, also known as your amplitude, which is A is a vertical stretch, is your vertical stretch and compression factor. So if A is greater than 1, for example 2, then your sine graph would be stretched by a factor of 2. If A is between 0 and 1, let's say 0.5, then it is compressed vertically by a factor of 0.5. If A is negative, it is reflected in the x-axis. Next is the k value, your horizontal stretch compression factor. It is sort of the opposite of the a value. If the value is between 0 and 1, it is stretched horizontally. If k is greater than 1, then it is compressed horizontally. So you can see in all of these graphs, this being your base sine graph, you can see in the next graph here that your maximum and minimum point have been stretched. So you could say that this is vertically stretched. Or you could say that it was horizontally compressed over here. So these look the same. However, your k value also affects your period. So the period of a standard sine graph is 2 pi radians. Here, the period you could say is pi radians because there's 2 cycles that occur in this graph. So you can see that it repeats more frequently. The next is phase shift, your d value. Phase shift is just how much the graph moves left to right. So here, with reference to your base sine graph, you can see that the graph has moved pi over 2 radians to the left. Next is your c value, which is your vertical translation. It's how far you move up, down. So in relation to our base sine graph, you can see that this graph has been moved 1 complete unit in the upwards direction. That is it. Now we're ready to get to our example. There's 3 steps. The first step is determining the max height. So I mentioned earlier that the max height has to do with your a value and c value. So we're going to add them together, a and c. 8 and 2. So 8 plus 2 is 10. So our max height is 10. Next, we're going to sub 10 in for y. So into our equation for y. So we sub 10 in, we bring 2 over, becomes 8. We divide by negative 8. We get negative 1, so negative 1 equals sine of 2x plus pi over 4. We're going to have a let statement, so let w represent 2x plus pi over 4. So sine of w equals negative 1. So we take the inverse, sine inverse of negative 1, and we get negative 90. So w equals negative 90. W also equals that. So we bring it up here. Negative 90 equals 2x plus pi over 45. We're going to divide by 2. Negative 45, x plus pi over 45, bring the pi over 45 over. We get x equals negative 90, which in turn is x equals negative pi over 2. Now our domain is between 0 and 2 pi. Negative pi over 2 is out of our domain. So what we're going to do, our third step, we're going to add a period, pi. The reason why it's pi is because our horizontal compression factor is 2. So we add pi. So negative pi over 2 plus pi equals pi over 2, which is one answer. Next, we're going to add another period of pi. So we get pi over 2 plus pi is 3 pi over 2, which is our second answer. So, again, our maximum height occurs at pi over 2 and 3 pi over 2, and that max height is 10. Some applications of sine graphs include sound waves, designing roller coasters such as Behemoth, or an engine. The pistons in an engine turn a crankshaft. Really, anything that has a change in velocity or like changes in vectors, you can apply sine graphs towards them.